and that is Dr. Vivek Dwivedi. He's the Associate Branch Head with the Thermal Engineering and Analysis Branch at the NASA Goddard Space Flight Center, focusing on thin film applications and research utilizing atomic layer deposition for thermal, optical, and additive applications. He received his PhD in chemical engineering from the University of Maryland, College Park, where his focus was on a novel multi-scale model of an atomic layer deposition process in high aspect ratio geometries. Dr. Dwivedi's research interests include reactor design, energy storage, spaceflight optics, gas sensing, catalysis, and engineering education. During his time at NASA, Vivek has matured multiple technologies, including passive thermal films, tuned nanopillars, applications in 3D carbon nanotube growth, and modification of pigments and powders. Dr. Dwivedi is a native Washingtonian who is actively involved in numerous organizations, including the American Institute of Chemical Engineers, National Capital Section, and holding positions of chair and director. Welcome, Dr. Dwivedi.
Well, thank you very much for giving me the opportunity to speak today about a topic which is very dear to my heart. And as you clearly heard from the bio, thank you very much, on atomic layer deposition. ALD, which is short for atomic layer deposition, it's what's known as a thin film process analogous to chemical vapor deposition. We'll be talking about that. More specifically, today's talk has to do with the utilization of atomic layer deposition to modify radiator pigments, specifically for charged bleed-off applications. Again, my name is Dwivedi. I'm with the NASA Goddard Space Flight Center, and I'd like to also recognize Mark Hasegawa as a co-author on this paper as well, who is a part of the Coatings and Contamination group, also at Goddard. So if we start talking about why exactly we're interested in modifying radiator pigments, we need to take a much more broader view. That has to do with the sun-earth connection. So we have obviously our sun, and our sun is a very complex in terms of heliophysics, in terms of the dynamics of its process. And what ends up happening is that from the sun, you end up with a coronal mass ejection. And from the coronal mass ejection are what are known as primarily solar wind. And your solar wind are composed of both, it's in general considered a neutral source having equal number of protons and electrons. And that solar wind then interacts with our magnetosphere, which is a reason why we have a magnetosphere is because of the iron core of the Earth. And that magnetosphere, along with the bow shock region of the magnetosphere, results in a shielding type of effect, which protects us from the solar winds. However, the dynamics of the sun-earth connection lead to the solar wind to go through the plasmasphere that's surrounding the Earth. That plasmasphere can wreak havoc on some of our assets, which are so based on that plasmasphere, we end up with an issue of spacecraft charging. Space charging occurs, or surface charging occurs from the low energy plasma more specifically during the eclipse, while we're in the shadow of the Earth. Phase of an orbit of the spacecraft may negatively charge to tens of kilovolts, and once the satellite emerges into sunlight, a photoelectric emission may occur, resulting in a potential discharge. So pretty much it's this idea of going from daylight to nighttime, which can lead to these arcing type of events. Another thing to keep in mind is as our spacecraft or as our asset is orbiting the planet, and due to the different masses of your protons and electrons, you actually end up with a charge misbalance within the structure of the spacecraft, where the ram direction is more positively charged, and your tail of your spacecraft is more. This interaction can lead to arcing events, which can occur. And so here are some examples of arcing events that can occur. And this, obviously, is hazardous to our assets in orbit. what we see here on the bottom are two images of arc damage which can occur. The bottom left is a satellite array, which has sustained arc damage, and that's courtesy of ESA. And the bottom right is arc damage in a laboratory test of material covering the ISS or shields. So it's very important that you develop technology that prevents this type of damage from occurring and getting these type of issues. So, moving on, let's talk about the radiator itself and what the focus of this talk is going to be. We're all thermal engineers. This is a thermal fluids workshop over here, and we all know that the radiator is structure in space. So coatings to maximize heat. And it may be coated with higher low solar absorption solar sources. If not an existing structure, then obviously support some need for these radiators. Now, typically for coatings, how do we apply coating on these radiators to meet those emissivity and solar absorptivity values? Films, tapes, paints, etc. applied to these radiators to meet those thermo-optical properties for that thermal control. And in terms of those thermo-optical properties we talked about, those are intrinsic to the material, the coated material, where we have obviously solar absorptivity, which is a percentage of the sun's energy, which is either reflected or absorbed. Then, of course, you have higher emissivity, which is the percentage of and injected into space. So one of the main interesting things about these pigments, these coatings, is the ability to beat off any sort of charge which is accumulated on these structures, and what is, and specifically what the resistivity has to be in order to meet those charge bleed off requirements as a function of the project itself, the mission itself, which dictates exactly that. But so if we take a closer look at the coatings for these radiators, on the left is your typical Z93 coating, which has an emissivity about 0.92 and absorptivity about 0.13. This is from AZ Technologies. And what we can actually see, if you have a closer SEM image of one of these particular coatings, you can see that there is significant topography associated with these pigments. And what we want to do is take advantage of these significant topographies. The idea that this powder itself, we can have a surface that we can actually dedicate and work on in some requirements we want in terms of charge distribution. So one of the biggest issues that we're interested in our radiators, and something to keep in mind, is that the radiators obviously vary in size. On the left, we see our space station radiator systems, which are obviously critical components of the active system, and several panels, each are 6 by 12 feet. In the middle, we see a wide field planetary camera 2 that was installed on Hubble December '93 and is moved during the last service mission in 2009. And what you actually see, those holes inside the radiator are actually micrometeorite bombardments. So had the opportunity, not I specifically, but at Goddard had the opportunity to core out some of those micrometeorite impacts to actually visualize and analyze impacts.
Hi, Vivek. I'm sorry to interrupt,
Sure.
but your microphone's going in and out a little bit, and it's hard to hear you.
Okay, let's see what I can do. Is that better? Or is
Yes.
it still down? Okay.
No, that sounds better.
Okay. Are you sure? Yeah, please. Thank you for letting me know about that. And if I start
no
breaking
problem.
apart again, I will do something in order to make sure it's right.
Fantastic. Thank you.
Yep. So moving on. So if you missed what I was talking about, really simply stated, radiators vary in size from really, really big structures to something as small as these origami-inspired radiators. That's all the way onto your right. So moving forward, we've talked about radiators, we talked about pigments. Now let's talk about what exactly are thin films. The way I like to define thin films are films which are typically less than 1,000 nanometers. Some of the special properties of these thin films are they're different from the bulk materials. It may not be fully dense. It's typically under stress as they're so thin. And they have different defect structures from the bulk. Because they're thin, they're going to follow what's happening on the substrate. And because of that, they're typically quasi-two-dimensional, and they're really, really strongly influenced by the surface. Now, what you see here on the bottom are three typical thin film type of technologies that are utilized for multiple applications. One on the left is what's known as the CVD process, and pretty much what happens is you have two separate gases which are in the chamber. They react in the gas phase. The byproduct of that reaction then reacts with substrate. Your substrate could be anything: radiator, powders, pigments, is a difference. And that byproduct of the gas surface reaction reacts with the bare substrate. That also goes through what's known as a gas surface reaction, and then that results in another byproduct being released. So how thick of a film are you creating? Well, your film thickness is based upon how much gas we continuously flow to the reactor so this process can be. So it's a function of time. The middle thin film process is your sputtering process, where your top green is your sputtering target. You hit that with a high energy argon source or something with high energy, which creates a bombardment of your sputtered target. And basically it's this sputtered target, which is this pulverized target, which is all over your vacuum chamber, and then that reacts with your substrate. And again, thickness is controlled by how long you continuously bombard that substrate with that argon source or that high energy source. And finally, your third way of depositing material is through evaporation, where you have a heated material and you are subliming the material through heat, and that sublimed material that to cook the material with, and thickness of the material. Again, it's a function of how long we actually continue the material to. In all those particular cases, the previous three, there's a common denominator. Obviously, the deposition only occurs in substrates that see the target. You do have a plasma process which can damage that substrate, which could be very dangerous. You have poor thickness control, poor step control, and you need a high pressure, high temperature environment. Actually, that should be a high vacuum, high temperature environment. So here is an example for what a step coverage looks like. So if you have like a 90-degree type of step, what you want to have is a very conformal material that wraps around that step. But what you end up seeing is a material which is not conformal. So you end up with grooves and not a uniform thickness. Talk about conformal and non-conformal type of coatings. If you have something which is like a trench or which has grooves and divots inside of the surface, what you end up seeing is something that doesn't completely cover beautifully that particular structure. What you end up having is material which is not uniform. So you have thinner walls, thicker walls that can lead to issues when you're dealing with high aspect ratio geometries. So one technique that can be utilized in order to meet some of those requirements, which are proper step coverage and being able to deposit things uniformly, is this idea of atomic layer deposition. What atomic layer deposition is, it's pretty much we take that CVD process and we break it apart. So instead of introducing two gases at the same time, we introduce a singular gas one at a time inside of our chamber. And what ends up happening is that only that particular gas reacts with your substrate, and what that's known as a gas surface limiting reaction. So pretty much once all your sites have been reacted with, you can no longer have a reaction. Then you introduce a second gas. So the best way I like to describe this is through a basic analogy. One of the gas, if we take a look at a Velcro has two surfaces which allow them to stick. One is your loops and the other one is your hooks. So imagine that one of the gases creates nothing but your hook surface, and your second gas creates nothing but your loop surfaces, and you continue going down this process until you a material which is thick enough to meet So this is what's known as a digital process. These particular reactions are benign to temperature to about 250 degrees C, and you don't really need a high vacuum. Regular vacuum is good. So some of the great things about atomic layer deposition is the idea of uniformity. So if we were to take the idea of what you talk about, these loops and these hook processes, the equation form is, you have one of the gases plus a second gas here, precursor A plus precursor B. B gives you a solid film. And cyclically speaking, the way it works, you introduce your A precursor, you create a purge, and you introduce a B precursor, you create a purge. And you continue down this process until you get your material. So if we were to take a silicon wafer and we would expand it to the size of the DC metropolitan area, pretty much what we would see is a uniformity of about 60 microns across this wafer. So the uniformity is spectacular for this type of manufacturing process. Additionally,
Hey Vivek, I'm sorry to interrupt you again. It seems like your audio is cutting in and out or fading in and out. Perhaps if you can maintain a closer proximity with the mic, I'm not sure if that would solve the issue.
Give it a second. All right, can you hear me?
Yes, that's better. Thank you.
Is that better?
I believe so. It just seems to be kind of fading in and out as you're talking.
All right, let me try this. All right, so let me know if I'm fading again.
Okay.
All right, so talking about the epitaxial growth, what we see here is that through ALD, we can actually create these multi-layers of material with precise thickness. So you have a silicon wafer, then you're going alumina, trinitrate, alumina, so you can create these sandwich wafers. You can do batch processes. This is an example of silver jewelry, which is being covered with alumina in order to prevent oxidation. That's a protective layer that's being created. And on the bottom left, you can see some nanoparticles which have been coated with some sort of material. And then you have the idea of being able to create these nanopillars through these molds of these using nanomolds pretty much. So moving on, in terms of ALD material systems, there's a lot of materials that we can actually coat. Metals, metal oxides, metal nitrides, metal fluorides. And this is just an example of a periodic table which has many of these materials which are currently being investigated and have been published in terms of use. So moving on, one thing that we were interested in is, these radiators vary in size, and if we want to add some sort of charge dissipating coating on these radiators, so typically what ends up happening is you coat your radiator with your specific thermal coating, then you put it inside of a big oven, and then you put an overcoat of, say, a charge dissipating coating such as indium tin oxide or indium hydroxide. And now, so pretty much what ends up happening is, again, depending on the size of your radiator, you pretty much need to have a vacuum system which allows you to put that entire structure inside a chamber, and that can be cost prohibitive. So the idea that we came up with is that instead of actually coating the entire radiator in the beginning with indium oxide or any of the charge mitigating coatings, is that we can actually then coat the pigments themselves in the powdered phase before binding onto the radiator, as a way of providing that charge dissipation path. So the way we're able to do that is, this is our typical little reactor that we have, is that we have these pigments inside of a rotating mesh basket. So the pigments are being rotated, and we inject within this chamber our two materials which allow us to grow our charge mitigating coating. In this particular case, it's going to be indium oxide. It's an interesting thing about the way that we operate. The rotating basket itself is nothing fancy. We actually ended up going to IKEA and utilizing a tea basket in order to hold our pigments, and it worked out just fine. So back of the envelope, what I call dirty engineering. So moving on, so the materials that we actually use, what are called precursors for our work, for indium oxide or tin oxide, it's called trimethyl indium and ozone, and the other one is tetramethyl dimethyl amino zinc and ozone. So what we wanted to do is actually dope about 5% of tin within our indium oxide mixture. And the way we're able to do this is what's known as a super cycle. So pretty much we went through an ALD process of indium oxide and ozone for X number of cycles, then we would throw in a single cycle of tin and ozone process of indium oxide. So going through the cyclical super cycle process, we ended up with a very specific percentage of tin doped indium oxide that we can actually apply to our pigments themselves. So in terms of experimental procedures, what we ended up doing was we loaded up a pre-weighted amount of pigment within our basket. We then rotated the basket for X revolutions per minute. Then we also had a dummy silicon wafer and a glass slide as well. And we went through the indium oxide, tin oxide process, and we went through spectrometry and 4-point probe measurements in order to determine how well of a charge bleed off or resistivity measurements, resistivity that we had across our film structure. So taking a look at the pigments themselves and what we could actually do. So we ended up doing was going through an SEM process where we took our pigments, which is can be visualized in the box A, and we went through an elemental analysis, which is B, C, and D, where we were able to scan for zinc, indium, and tin, and oxygen. And here we can actually clearly see that we were seeing all the various elements within our structure. In fact, I believe for this one, this is only for indium oxide. We do have one for tin. But this gave us a very good representation, gave us a very good colorful map of the various elements. So moving on, this is what actually the pigments look like after they've been coated. So the picture on the left is your uncoated pigment, which is your bare Z93. And your pigment on your right is your coated one. So you can actually see a very nice roughness, some topography within the surface dynamics of the pigment itself. So moving on, so one of the main things we're interested in is that if we apply these thin films to these pigments and what exactly happens optically speaking. So we went through some optical analysis and we found that reflectance of a function of wavelength pretty much were spot on. We had a very, very small change in the reflectance measurements. And in terms of your absorptivity and your emissivity coatings, we basically saw that we really did not change the optical properties. I think everything we see in terms of those absorptivity, emissivity values are within the error of measurement. So moving on, so one thing we were able to do is find out what happens in vacuum. So we were able to take these pigments, both your coated pigments and your uncoated pigments, put it through a compression process and put it in vacuum to measure the resistivity across these pigments. And what was interesting to note is that as we increased our vacuum, your resistivity decreased by 3 orders of magnitude once we reached 10 to the minus 2 joules. And the resistivity that you're seeing for 10 to the plus 2 to the 10 to the minus 2, many of it is your outgassing of your water, which is a huge concern when it comes to some of these powdered and resistivity measurements. With these high vacuum, we're actually being able to remove moisture content within the bulk powders. So as we go to much higher vacuum, we get a much more accurate result of your resistivity from. So one of the great opportunities that we had was to determine how well these particular coated pigments and uncoated pigments would, how their optical properties would be affected in the environments of space. So we went through an ISS opportunity CFF project, which occurred, the launch occurred last year, a year and a half ago actually, and currently it is on the NISI FF carrier being exposed to environmental conditions on the ISS. The great thing about this opportunity is that we do get our films back, hopefully the next couple of months, to verify the absolute values of films. At the same time, further verify that charge dissipation properties. I'd like to finish up my talk by saying many thanks to Mark Hasegawa and Ray Adamides from the University of Maryland. And with that, I'd be more than happy to answer any questions that you might have in regards to this talk. Thank you.
Yeah, thank you, Dr. Dwivedi. Really appreciate it. Yeah, Bill, do we have any questions on the live stream?
All right, let's take a look here and refresh it here for a moment. Give me a second. A few issues. Okay. Doesn't appear we have any new questions for this presentation yet on the live stream. Let's give it a minute or so for people to catch up. Okay, we've got a question here. So how well can you verify that you have coverage of the ITO on the surface?
Right, so one way that we can verify that we have good coverage is either one, go through our SEM process where we can actually visualize what is going on with the pigments themselves. The other way would be through actually going through the coating process. So we bind the coated pigment with our binder. We go through a spray process, and then we can just go through a very simple 4-point probe type of measurement across multiple regions within our substrate to verify that we actually have conformal coating and a good coating across our surface.
All right, thank you. Here's another question. I've got two more questions. Does the ITO influence the degradation?
That's a very good question. So what we're hoping that the ITO does not, and we'll find out once we get our samples back from the NISI FF flight experiment. What we're hoping is that the optical properties remain constant, and the charge lead-off properties also remain constant during the 1.5 to 2 years of exposure time that the films will be seeing
All right. And the second question here is, does ALD increase resistance of ITO to be removed by any casual brush or either during manufacturing or by astronaut interaction?
Yeah, so what we like to do when it comes to ALD, so ALD is a pretty robust process. And as I had shown previously, it is utilized in the semiconductor industry. It's also utilized as a protective coating, as an example, when it comes to environmental effects on silver. So you can actually try to rub it off with your fingers, and it won't rub off. So you actually have to go through more of a chemical etch in order to try to remove some of these materials. The other thing that we actually utilize is a very simple tape test, where we will coat, say, ITO or another material on a glass slide or a silicon wafer, and we'll go through surface analysis and do a very simple tape test to see if we have any removal of material. And going through that process, what we found is that the ITO is very robust, even through day-to-day handling of the material.
All right, thank you.